Good morning. In this video, we're going to talk about the basic differentiation rules. I'm just going to review those that we've discussed in other videos. Then I'm going to state the basic differentiation rules for the natural log, the log base of a of x, the inverse trigonometric functions. We're not actually going to derive those until after we learn the product rule, chain rule, and implicit differentiation. But we will do those derivations later after we have some more skills under our belt. But for now, we're just going to sort of build our list of basic differentiation rules so you guys can make flashcards and make sure that you start practicing them. I think we have about 20 rules, a little bit more than 20 rules. I want you to commit those to memory so that it's easy to efficiently compute derivatives for the rest of the semester. So that's the plan. Okay, so our basic differentiation rules are these. We have the derivative with respect to x of a constant is 0. And that makes sense because we draw a constant function. Say y equals 3. And the derivative is just the slope of that line. The derivative or the slope of a horizontal line is just 0. Similarly, if we take the derivative with respect to x of a constant times x, that's just the slope of a line that passes through the origin. The derivative of a constant times x is just the constant because the slope of a line that passes through the origin is just the coefficient of x. We know that. We can sketch a line like this. So if our line happened to have a slope of 2, then the derivative would be 2. And then let's see what else. Other rules that we need. The derivative of a constant times f of x is a constant times the derivative of f of x. So the idea here is if we make the function, c times as tall as it was originally, and we know that this function is differentiable, then the derivative is just that constant times the function. That one actually might require a derivation. Let's say you know that f prime exists and you're looking for the derivative with respect to x of a constant times f of x. Well, that's just the limit as delta x approaches 0 of f, or excuse me, our function, which is c times f, evaluated at x plus delta x, minus the function, which in this case is c times f of x. And you notice that there's a common factor of c in the numerator. You can factor that c out. And then you see that this expression is just the definition of the derivative. Sorry, my camera's having a little bit of trouble this morning. Let's see. There we go. This is just the definition of the derivatives. That's f prime. So we end up with c times f prime as the derivative of c times f. And that's nice because if you have a constant multiplying a function, you can just factor that constant out and just multiply by the derivative of a function. Other derivative rules, we said the derivative of x to the n is n times x to the n minus 1. A very simple example of that is y equals x squared. The derivative of that is y prime equals. Now check out our rule. So you bring that exponent down, multiply by x to the 1 less power. So we bring the exponent out front. And then we've got x raised to the 1 less power, 2 minus 1 is 1. So that's 2 times x to the first, which is just 2x. So if we draw the line, we say that this is the slope of this. And we can tell it's consistent with our intuition. The slope is 0 here at the vertex of our parabola. And then all of the tangent lines on this side have positive slopes. If you were to draw them, they would all be increasing as you go from left to right, and the y values would go up. And so and the lines get steeper the farther you get from 0, x equals 0. So the slopes are increasing. It turns out that the slopes are increasing at a constant rate of 2. And then on the other side, we've got slopes that are decreasing, negative slopes, negative values for the slopes. We've got like a very large negative slope here, and then a slightly less negative slope here, and a slightly less negative slope. Eventually, you're going to have like a slope of negative 1/2, and then you're going to get to 0. So basically, you've got a bunch of slopes that are negative. which means our derivative values should be negative. And because they're larger in magnitude here, because the lines are steeper, those absolute values should be much larger. So if the slope here was -10, I would plot the point of x equals whatever that x value is, y equals -10 on the derivative graph. But this is just a straightforward application of that rule. We've got a rule that the derivative of f plus g of x is equal to f prime of x plus g prime of x. That makes it really easy to compute the derivatives of sums of functions. You just take the derivative of the first function and then add the derivative of the second. This, combined with this rule, allows us to take the derivatives of polynomials relatively easily, especially if we've got things like this. You've got derivatives of powers here, derivatives of constants times x here, derivative of constants. So that all three of those combined with this rule and this rule make it very, very easy to take the derivative of a polynomial. Let's see, what else? What other rules? We could also subtract them, same thing. Let's see. And in the last couple of videos, what did we talk about? We also talked about the derivatives of our trig functions. So we had the derivative with respect to x of sine of x is cosine of x. Now, I'm not going to graph these because in this video, we're just trying to review our basic differentiation rules. The derivative of cosine of x turned out to be negative sine of x. We derived both of these derivatives algebraically, and we explored their graphs geometrically and sort of inferred what the derivative should look like by looking at slopes of tangent lines. We did something similar with the derivative of tangent of x that turned out to be secant squared of x. We proved that algebraically as well as doing that graphical exploration. And then these three I just told you. These three we will derive later once we have the quotient rule under our belt. Turns out that there's a rule for the derivative of a quotient. That's going to make computing these three derivatives very easy. Because secant, cosecant, and cotangent are really just quotients. We'll actually be able to derive the tangent derivative very easily as well. Now, one rule that you can use, or sort of a mnemonic device, is that the derivatives of the cofunctions are negative. So derivative of cosine is negative sine. Derivative of cotangent is going to be a negative function, or a negative times a function. The derivative of cosecant is a negative times a function. And the derivatives of these guys kind of mirror the derivatives of these guys. Since the derivative of tangent is secant squared, if you do the calculations for cotangent, it turns out you're going to end up with a negative cosecant squared. It's almost like I just took a CO and I tacked it on this function and then multiplied by a -1. Now for the derivatives of secant and cosecant, turns out that the derivative of secant of x is secant of x times tangent of x. The derivative of cosecant is negative cosecant of x times cotangent of x. Now again, we're going to do the derivations later. If you want, it's a good idea to graph these functions and their derivatives and convince yourself that the slopes of the tangent lines of these functions are given by the values on these functions. Again, we're just going to do that later. For right now, I'd just like you to add these rules to your flashcards. So we've got those. And then we also know that the derivative of e to the x, that's the easiest one, is e to the x. Super easy. The slope of the function is actually the function itself, which is kind of cool. And the derivative of a to the x, of course, we're assuming a is not equal to 1. Actually, if a was equal to 1, the identity would still hold, but it would be the derivative of 1 equals the natural log of 1 times a to the, or 1 to the x, which would be 0, natural log of 1 is 0. But the derivative of a to the x in general is natural log of a times a to the x. So if the base is something other than e, we actually do that computation, or excuse me, not computation. And we have to multiply this by this extra factor, and that extra factor is natural log of a. When a is greater than e, this just takes the original function and rescales it by a factor of natural log of a. It's going to make it taller. If a is between 1 and e, then it makes the graph sort of smaller because between 1 and e, well, we get values that are between 0 and 1. So we're taking a fraction between 0 and 1, multiplying by a to the x, so it just sort of shrinks the graph vertically. And then if a is between 0 and 1, then natural log of a is negative, and so it sort of flips the sign of the derivative. This is a negative value. But in application, whenever you see a problem, let's say someone asks you to compute the derivative of 2 to the x, you literally just write natural log of 2 times 2 to the x, which is super simple. You just say a equals 2, and then you apply the rule. Very, very easy. Okay. Now, the other rules that we'll talk about are these. Now, I'm just going to write them down, and we will derive them once we learn the chain rule and implicit differentiation. It turns out that the derivative of natural log of x is 1 over x. And of course, here, when we're assuming that x is positive, so that's for x greater than 0 as well. The implied domain here is the implied domain there. And the derivative of log base a of x turns out to be 1 over natural log of a times x. So we just end up with this extra factor of natural log of a here, just like we ended up with a extra factor of natural log of a here. It's because of the relationship between this function, and this function that we get this result and this result. Now, in practice, this is really simple to evaluate. Let's say somebody asks you for the log base 3, or the derivative of log base 3 of x. You just write 1 over, you identify a as 3, natural log of 3 times x. Easy breezy. So you've got these two, and then what are the others that we wanted to cover? Oh, the inverse trig functions. Now these are going to feel like just straight memorization. I'm going to say, how on earth will I ever memorize those? Well, you'll see the derivations and then it'll become a lot more obvious, but we won't actually do those derivations until a little bit later. But I wanted to have these on your formula sheet so that you can compute those derivatives, even if you don't have the derivations in mind yet. It'll be a lot easier to memorize them when you actually know where they come from. It's weird that I accidentally skipped our arctangent. Very weird. Someone had me switch those or something. It's weird. Arcsine, arccosine, arctangent, arccotangent, arccosecant, arcsecant. It's a slightly different order than I'm accustomed to writing them. Okay. So it turns out that the derivative of arcsine of x is 1 divided by the square root of 1 minus x squared. And the derivative of arccosine is exactly the same as this, but it's multiplied by -1. Now for the derivative of arctangent, which is usually the one I would write next, I get 1 over 1 plus x squared. The derivative of arccotangent is -1 over 1 plus x squared. So those two functions go together, and the ones with the CO in front have the negative result, the negative derivatives, or the negative in the derivative formula. The arcsine and arccosine look the same, but the arccosine is negative. Arctangent and arccotangent look the same, except the arccotangent is negative. And then arcsecant looks like this. So you've got the absolute value of x in the denominator and the square root of x squared minus 1. For arccosecant, you've got a -1 divided by the absolute value of x times the square root of x squared minus 1. So we're going to cover all of those later again. All right, so now we have all of these rules. We've got our 6 derivative rules. We've got our 6 derivative rules for trig functions, and then 6 derivative rules for the inverse trig functions. We've got our basic rules for derivatives of constants, derivative of constants times functions, power functions, exponential functions, sums and differences of functions, and the logarithmic functions. This is our basic rules sort of sheet. I made a PDF, and for some reason I can't find it. But it looks roughly like this. It doesn't have the pictures, but it looks roughly like this. These are the ones I would have you commit to memory. And the reason why we do that is because we need to be able to compute derivatives efficiently. I teach differential equations, and when I teach differential equations, we use something called the method of undetermined coefficients frequently. The ability to compute a derivative efficiently is one of the most important skills that you have in order to be able to actually finish those problems within the time constraints of the course. For example, if we have a right-hand side that has an exponential function times a trig function, we end up guessing the form of a particular solution to the differential equation, and we have to take the first, second, and perhaps even third derivative, and then substitute that into the left-hand side of the equation, simplify. I mean, it takes a long time. The computation is relatively simple, though, if you know your rules, but if you don't know your rules, if it takes you 30 minutes to compute a derivative, we're going to have a problem. So it's very important that we actually know how to compute these, or how to apply these rules efficiently. And for these, we're just going to rely, at least initially, on memorization, which is much more efficient than that limit definition of the derivative that we talked about earlier. Now, for the derivative, we have got 3 more derivative rules that are on here, or that aren't on here yet. And those are going to be the subject of the next few videos. If we have a product, f of x times g of x, the derivative of the product is the derivative of the first function times the second function plus the derivative of the second times the first. And we will apply that in the next few videos. Then we have the derivative of a quotient, which turns out to be the derivative, or the bottom function times the derivative of the top function, minus the top function times the derivative of the bottom function, all divided by that bottom function squared. Actually, I think I'm going to write it like that. Sometimes we call this high and this low. Then we say this is low d high minus high d low over low low. We're going to do that later. And then finally, we've got the derivative of a composite function. And the way we take the derivative of a composite is we evaluate the derivative of the outside function at the inside function. And then we multiply by the derivative of the inside. And usually this is not written this way. It's usually written f prime of g of x times g prime of x. This is called the chain rule.
Really, it's just a little bit.
And then once we learn the chain rule, we'll be able to talk about implicit differentiation. We're also going to learn about some other functions called hyperbolic functions. We'll learn those derivatives as well. And remember, all of these derivatives are formulas for the slope, or formulas for instantaneous rate of change, and we'll interpret those in applications. I would suggest, if you're trying to memorize this list, make some flashcards. Put this on one side of the flashcard, this on the other side of the flashcard. The derivative of the function on one side, and then it's the actual derivative, the answer, on the other side. And then make sure that you know the rules. And then in no time, you're going to know all the rules and be able to apply them. So very, very simple, very, very easy. Yeah, and we'll do more of that in future videos.